Who wants to win 1 million? Answer this. Are every non-trivial zero of the Riemann zeta function lie on the critical line? Everyone who have learned calculus should be familiar with mathematical curves. This one is exquisitely beautiful, but uniquely complex. It has haunted mathematicians for centuries. What you are seeing is the path of the Riemann zeta function going at the critical line. The zeta function is the centerpiece of the actual $1 million problem. The statement is very simple. Find a counterexample, win 1 million. Prove if above is all true for all, win 1 million. We managed to prove that first dozen trillion zeros are on the critical line. The function will exhibit complicated patterns at higher heights. We see the loops getting further and larger from the origin. We also see extremely tight loops referred to as the Lehmer phenomenon. The largest loop of the zeta function is more than 16,000 units from the origin. This video is recommended to those who already watched 3 blue, 1 brown zeta and analytical continuation video. However, our video is the first of its kind to quantitatively characterize the function at the high heights. This requires both computational and mathematical optimization. The animation and calculation is generated by NVIDIA CUDA code, enabling CG GPU that's powering today's AI boom. In fact, at the time of the video, NVIDIA is the largest company by market capitalization. The zeta function. At the end of your introductory calculus class, you learn to approximate special functions with a power series. A function like sine or exponential function can be approximated with polynomial of their variable or a shifted version. The last one is the power series formula for the geometric series, except sum is valid only for modulo x less than 1. The rational function, analytically continuous power series, originally defined on the open interval. What if we switch x and k around? We now have what is an equivalent to the Dirichlet series. We have a weighted sum of all the x power of the natural numbers excluding 0. The Riemann zeta function actually began its life 288 years ago by Euler, famous for the formulas that allowed rotation to be expressed algebraically, e to the power e in the power of I times pi equals 1. It is the Dirichlet series with all coefficients set to unity. He also solved the case for x equals 2 for the zeta function equals pi squared over 6. He is also the first one to connect the zeta function to the zeros by performing an algebraic set of equations. Each 1 over px term mean include only multiples. Likewise, 1 minus 1 pi over x mean exclude only multiples. It isn't the existing list. Eventually, for every n greater than 2 will be excluded under this function. Euler discovered product form of the zeta function. However, our zeta function is only defined for the real values strictly greater than 1. Over a century later, Bernard Riemann investigated zeta function for the complex values, now denoted as in the literature. However, the series converged only for s with real part greater than unity. Now turn all even terms negative and analyze the product formula. Now new s is now conditionally convergent on the critical strip, including the right boundary. We analytically continued the zeta function to the right half plane. It is where the truly unusual character of the zeta function has been identified. In fact, for any holomorphic function there is one and only one analytically continuous, and the domain might be imaginary for any function. Furthermore, the domain might be limited or might even depend on the path you take to analytically continue the function, Riemann surface. Finally, the zeta function can be analytically continued on the complex plane. There is a pole at s equal 1, analogous to the Dirichlet harmonic series. It also reveals the zeros at the negative even integers through sign called trivial zeros, while the product formula reveals no zeros with real part unity or greater. The functional equation allows us to compute zeta function on the left half plane, including imaginary line in terms of the zeta of the complement, which is already defined. It is the ratio of 2 to the s against pi, s complement times the product of the sign of the number of quaternions, the gamma of the complement, and zeta of the complement.